I welcome you all in the course Refrigeration and Air Conditioning, and today we will discuss on compound compression with intercooling in a refrigeration system. Now, in a refrigeration system, the major part of energy consumption is in the compressor. If I draw on a pressure enthalpy diagram, then in a compressor, and 1. So, we get refrigerating effect in process 4 to 1 at the expense of the energy during process 1 to 2. And that is how we calculate the COP, how much refrigerating effect we are getting H1 minus H4 and how much energy we are spending to get this refrigerating effect. Now, if anyhow, if we can reduce the energy consumption during compressor process, if we are able to reduce the energy consumption in this process, automatically the value of coefficient of performance will increase. In a reciprocating compressor, if I take a simple reciprocating compressor, that is 1, 2, 3, 4. The energy consumed is the area of this diagram, right. Now, instead of compressing from state 1 to 2, because what happens when we are compressing from state 1 to 2, the temperature of the refrigerant keeps on increasing. When the temperature of the refrigerant keeps on increasing, the enthalpy of the refrigerant keeps on increasing, right. Now, what we can do, if we tap the refrigerant in the middle of this process 1 to 2, and cool it and again compress it. So, 2, 3, this is 4, 5 and 6. It means we trap the refrigerant in the middle of this process 1 to 2, cool it to initial temperature. So, cool it, that is known as perfect intercooling. Perfect intercooling means the gas is trapped in the middle of the compression process and then it is cooled up to initial temperature T1. So, T5 is equal to T1. T1. So, instead of having two compressors, instead of having one compressor, if you use two compressors, one compressor for process 1 to 4 and another compressor for process 5 to 6. Instead of using one compressor from state 1 to state 2, if you are using two compressors and one heat exchanger, we can save this much of energy. So, multi-staging is done normally in the refrigeration systems in order to reduce the power consumption in the compressors, and there are certain other benefits also, and we will discuss those benefits in subsequent lectures. Now, starting with the most basic process, this is 1 to 2, 3, 4. Now, now the point is at what pressure we should compress, what should be the value of P4 or what should be the value of P4. If we take the value of P4 less, in that case we will be consuming more energy here. But so, in order to find the pressure at P4, let us do one short derivation that work done in process 1 to 4 is in a reciprocating compressor, it is going to be equal to N upon N minus 1 P4 V4 minus P1 V1 divided by, this is okay. So, or N upon N minus 1 P1 V1 P4 by P1 raised to power N minus 1 upon N minus 1. Is it clear? So, this is the process 1 to 4. Now, process 5 to 6 is again we can write N upon n minus 1, index of compression is remaining same, P5 V5, again P2 by P4 raised to power n minus 1 upon n minus 1. So, work done in this process is this, work done in this process is this. Now, total work done. Now, total work consumed during compression from state 1 to state 6 is W 1 to 4 plus W 5 to 6 is equal to W dash or modified work. So, now this W dash is equal to work in process 1 to 4, that is n upon n minus 1 P1 V1 P4 by P1 raised to power n minus 1 upon n minus 1 plus n upon n minus 1 P 5 V5 P2, that is P6 is equal to P2 and P5 is equal to P4. So, we can always write that P6 by P4 raised to power n minus 1 upon n minus 1. We can take n upon n minus 1 common here, and since P1 V1 is equal to P5 V5, P1 V1 is equal to P5 V5 because temperature at state 5 is equal to temperature of state 1, right. So, we can always write P1 V1 is equal to P5 V5. So, we will take here common P1 V1 and inside the bracket will remain P4 by P1 raised to power n minus 1 upon n plus P6 by P4 raised to power n minus 1 upon n minus 2. Now, again for W dash, n upon n minus 1 we shall remain constant throughout the process. So, n upon n minus 1 can be taken as a constant A. So, n upon n minus 1 upon n can be taken as a constant A, and in that case W dash is going to be equal to 1 by A P1 V1 P4 by P1 raised to power A plus P6 by P4 or P2 by P4. We can always write P2 by P4 raised to power A minus 2 because P6 is equal to P2. So, here we will replace P6 by P2, so P2 by P4. Again we can use same old technique, that is differentiate this dW dash with respect to P4 and put it equal to 0, then in that case we will be getting is equal to 1 by A P1 V1 A P4 raised to power A minus 1 P1 raised to power minus A plus minus A P4 raised to power minus A minus 1 P2 raised to power A, and this will be 0. Now, here what we have done, we have this is constant P1 V1 and A are constant, we have differentiated the work with respect to P4. So, when we are differentiating it with respect to P4, then A x to power A x to power n minus 1. So, A P4 raised to power A minus 1, P1 raised to power A, when it will go up it will become P1 raised to power minus A, then P4 here is in denominator, then minus A P4 raised to power minus A minus 1 P2 raised to power A. We can further simplify it as A P4 raised to power A minus 1 P1 raised to power minus A minus A P4 raised to power minus A minus 1 and P2 raised to power A is equal to 0, because this is 0. If we want to find the value of the optimum value of P4. Now here A will be cancelled out and P4 A minus 1 P1 minus A is equal to P4 minus A minus 1 P2 raised to power A. Now this is going to be P4 A minus 1 plus A plus 1 is equal to P1 raised to power A P2 raised to power A, and this will be cancelled out. So P4 raised to power 2A is equal to P1 raised to power A P2 raised to power A, or we can write P4 is equal to P1 P2 under root, because this will give you P4 raised to power 2 is equal to P1 P2. From here we will get this, and from this we can derive P4 is equal to under root P1 P2. So if it is a two-stage compression, the intermediate pressure will be under root of the product of lower pressure and higher pressure, and this will give the minimum work input required, or in this case if we take the intermediate pressure as P4 as P under root P1 and P2, in this case the work consumed by the compressor will be minimum, or work done on the compressor will be minimum. However, because this sometimes we may get the odd value in case of, suppose we are not taking under root P1 P2, but the value is close to P1 and under root P1 P2. Suppose the under root P1 and P2 is 5.16. So instead of, and P1 is 1, I will give you one example. Suppose P1 is 1 and under root P1 P2 is 5.16. In that case P3 or P4, this intermediate pressure P4 can be taken as 5. So if we are doing this much of deviation, it is not going to affect much, it is not going to have much bearing on the power consumption by the compressor. Now I will take one live example. The application of this multi-stage compression in the case of refrigeration systems, where we have taken 1, 2, and suppose intermediate pressure, optimum pressure is P3 is equal to under root P1 and P2, and then it is subcooled to 4, and T4 we say that T4 is equal to T1. Now in this case the T4 is equal to T1 is only in the case when there is perfect intercooling, or after compression up to state 3 the initial temperature is restored in a heat exchanger. So the gas after compression will go to the heat exchanger, in heat exchanger heat exchange will take place and the initial temperature is restored. However, in the case of refrigerants, first of all this is not valid. There is a deviation in this, because refrigerant is not an ideal gas. So ideal gas equation we cannot apply to the refrigerants. However, if we use this concept, we will be getting the P3 very close to the optimum one, because ideally if we look at we will not be getting if we take in the case of refrigerants, if we take under root P1 and P2, we may not be getting exact value of P3, optimum value of P3, because we have assumption that there is a perfect intercooling, and for perfect intercooling we have used the relation P1 V1 is equal to P2 V2. But I have stated earlier, if there is a slight deviation in the pressure at state 3, the total energy consumed by the compressor is not going to be substantial. So suppose we are getting pressure at 3.71, so we can always go for 4. Ideally the energy consumed in both the states should be equal, but practically it is difficult to maintain. So if the inlet pressure is 1 bar, so instead of designing it up to 3.7 bar, 3.8 bar, we can design up to 4 bar. So 1 bar to 4 bar and 4 bar to let us say 15 bar or 16 bar. So work consumed by the compressor in both the stages, it will be different, and we will be using 2 different compressors for these 2 processes. in multi-compression system. Now, let us take an example. Suppose we want to have multi-compression starting from minus 30 to 50. The evaporator temperature is minus 30 and condenser temperature is 50 degrees centigrade and the working fluid is R134A. So, if the temperature difference is such between minus 30 and 50, now P1 is equal to 0.8434 bar and P2 is 13.179 bar, right. Now, P3 is going to be the under root of the product P1 and P2 and that is going to be equal to 0.8434 multiplied by 13.179 and P3. So, P3 is equal to, we will be getting 3.33 bar. Now, instead of going for 3.33 bar, because here it is 0.2 and then 0.3 and 0.4, we can comfortably take 0.3 bar or 3 bar as the intermediate pressure. So, the vapor is compressed from this point to this point and this line will be close to the parallel to the nearest isentropic line. So, we will extend this constant pressure line here and this line is parallel to this one. So, state 1 and then state 2. Now, this is not, we will not take state 2, it is taken as state A and state B. No, sorry, state B is this one. This is state B. So, state A, state B. Now, first of all, we will draw the simple cycle, state A, state B, then state C and minus 30. We will be getting here state D and state A. This is the original cycle without any multi-compression or intercooling, A, B, C, D. Then we will take up the cycle with intercooling. So, then it is heated, then cooled up to the saturation state and then the vapor is again heated and this cycle is H, F and G. Now, I am explaining it again. There is a original cycle which is operating between minus 30 degrees centigrade and plus 50 degrees centigrade. 50 degrees centigrade is condenser temperature, evaporator temperature is minus 30 degrees centigrade. Single compression from going from A to B, right. Instead of doing that, we have tried to find some intermediate pressure for multi compression. So, we have taken under root of P1 and P2, that is P2. This is 2 and this is 1. So, we have taken under root of P1 and P2 and we have got the value 3.33 bar. Now, 3.33 bar, instead of going for 3.33 bar, because this is for the ideal gas, we have taken 3 bar. Now, 3 bar can be easily shown on the pH diagram here. So, the vapor is compressed from this pressure to up to 3 bar, then it is cooled to the saturation state and then again it is compressed in another compressor. So, this is compression 1 and this is compression 2. We will be saving this much of energy, or we can say that the saving of energy can be taken as W1 minus W2, work done in this process. So, let us take process A, B, C, D. HA is equal to, if you read from here, it will come around 380 kilojoules per kg. If you can look at the screen of this PPT, you can get better idea about the values because this diagram is clearer. So, now SC is equal to HD and that is equal to 271, approximately 271 kilojoules per kg, and HB is equal to 445 kilojoules per kg. Now, in this case the refrigerating effect is HA minus HD. So, R is equal to HA minus HD, and that is 380 minus 271 is equal to 109 kilojoules per kg. If the mass flow rate is 1 kg per second, so it is going to be 109 kilowatt. Now, work in the process A to B is going to be 445, that is enthalpy at B, minus enthalpy at A, that is 380, is it going to be 65 kilojoules per kg. If the mass flow of refrigerant is again 1 kg per second, then it is going to be 65 kilowatts, and COP in this case is 109 divided by 65, that is going to be equal to 1.677. Now, let us take another case. Another case means when there is a multi compression. So, compression from A to F, from F to G cooling, and then G to H. Now, we have to get the two more values, that is HF and HH. So, HF is, from this diagram itself you will get 410 kilojoules per kg, and HH is going to be 428 kilojoules per kg. We also need the value of Hg, and Hg is 400 kilojoules per kg. These values you can take from a pH diagram which is shown on the PPT. So, now with the help of these values we can get the work in the compressor, that is HF minus HA plus HH minus HG, and work in the compressor here is going to be 410 minus 380, that is HH and HA, plus 428, we have taken from here 428 minus HG 400, and that is going to be equal to 30 plus 28, 58. This is the work kilojoules per kg of refrigerant. Now, here in this case the work is 58 kilojoules per kg, in this case it is 65 kilojoules per kg. Now, if this modifies the COP as 109 divided by 58, and that is going to be equal to 1.879. Now, if we compare these two COPs, this COP dash is higher than the previous COP by approximately 12%, and work consumed here in this case 65, this is 58, and this is reduction in the work consumed by approximately, this is approximately 10.8%, and or we can say 11%. By simple intercooling we have improved the COP by 12% or reduced the work consumed by the compressor by 11%. They are much more better system or smarter system which can provide these type of processes without any use of this intercooling heat exchanger. So, all those processes we will discuss in the coming lecture. Thank you.